Example 2. We will again revisit a system that we have already done earlier. We have a 3-dimensional 4-bar mechanism. The arm is rotating at omega 1 and is connected to the other arm AD through this link AB. This is a 3-dimensional problem. We are given that omega 1 is a constant, this rotation is a constant, and we need to find the angular acceleration of this link AD, which is called alpha 2, and the angular acceleration of the connecting link AB, which is alpha AB. When we did the velocity analysis of this system in lecture 10, we saw that the link AB could rotate in an arbitrary manner about AB. That means that this link AB can rotate about itself in an arbitrary manner. Therefore, in the velocity analysis, we could only find the angular velocity normal to the axis of the link AB. Here NAB was the unit vector along the axis of the link. Since we can only find angular velocity normal to this line, therefore it makes sense that we will also be able to find only the angular acceleration normal to this line. So let's now go ahead and try and solve the problem. We will begin as always with a velocity analysis. This we have already done in lecture 10. There we found that the unit vector NAB is given by this formula. Here in the picture I have indicated the various coordinate systems we had used in the velocity analysis. We also found that omega 2, which is the angular velocity of the link AD about the shaft, the vertical shaft, was simply omega 1, while the angular velocity's component normal to the link AB was given by this formula. Let's now begin the acceleration analysis. Here on the right, I have redrawn the figure that we are going to investigate. And let me remind you of the various coordinate systems we are using. We are going to use fundamentally two coordinate systems. The blue coordinate system centered at C, which is attached to the link BC, and the red coordinate system, which is centered at D and which is attached to the link AD. We will be making extensive use of the formula which connects the accelerations of 2 points on the same rigid body. So if P and Q are 2 points on the same rigid body B, then AP is related to the acceleration of AQ by this formula, where omega B and alpha B are the angular velocity and angular acceleration of the body B in question. Let me show you the accompanying figure for this formula. This was body B. Here were 2 points P and Q, and this was rotating at omega B and alpha B, and this vector was R P with respect to Q. Okay, so let's begin. As always, our general strategy would be to pick a point and write its acceleration in two different ways. During velocity analysis, we had picked the point A and written its velocity in two ways. Let's do the same here. So we will write the acceleration of A in two different ways. So here is the first way. Point A is a point on the link AD. So using this formula, identifying P as A, Q as D, we will get that AA is equal to AD plus omega AD cross omega AD cross RAD plus alpha AD cross RAD. Clearly the rigid body here is the rigid body AD, whose angular velocity will be omega AD and alpha AD. Let me call this equation 1. The second way that I will write the acceleration of point A will be to consider it as a point on the link AB. So I can write down that P must be A and Q must be B, so that AA is equal to AB plus omega AB cross omega AB cross RAB plus alpha AB cross RAB. Let's call this equation 2. We can now combine equation 1 and equation 2 and we will get this equation. Let's do a preliminary counting of the number of knowns unknowns in this equation. AD. Do I know AD? Yes, I do, because over here on the left D is a point on the axis and therefore AD is 0. Let me put 0 here. Omega AD I know because I just did the velocity analysis, and in the velocity analysis omega AD is simply omega 2 along the axis E2 prime. So omega AD is known. Alpha AD I need to find here on the left, alpha 2. AB, which is the acceleration of B, I do not know, so I put a question mark there. Omega AB I found, or at least I found the omega AB which is normal to the axis NAB, and as we will see, this will be the only part which will contribute to this equation. So let me temporarily write that I do know omega AB. Finally, alpha AB, well, that is one of the things I need to find. So we'll put a question mark over here. So if we count, we have 3 unknowns over here, 3 unknowns over there, 6 plus 3 unknowns over there, 9. I have 9 unknowns, but I only have 3 equations because this is a 3-dimensional vector equation. What am I missing? Well, the first thing is to notice that alpha AD is alpha 2 along E2 prime. That means I know the direction of alpha AD, it is along E2 prime. E2 prime is here on the left, a known direction. What I don't know is alpha 2. So actually alpha 2 is only one unknown. Then, as argued here during the velocity analysis, here on the left, we cannot find alpha AB in totality, but we will only be able to find alpha AB normal to the vector n, which is along the axis AB. That means alpha AB is basically 2 unknowns, because the component along NAB we will not find. Let's see. So we have now down to 1 plus 2, 3 unknowns plus AB. AB is again 3 unknowns. So we have still got 6 unknowns and 3 equations. So we need more information. Where is that information? That information is actually staring us in the face, because AB is also a point on the link BC, and we know everything about link BC. So therefore we can write that B is also a point on BC, so that AB is equal to AC plus omega BC cross omega BC cross RB with respect to C, plus alpha BC cross RB with respect to C. In this equation, AC is clearly 0, because here on the left C is on the shaft. Omega BC is given to us, it is omega 1 along E1. Alpha BC is given to be 0 because omega 1 is a constant rate and the direction is also fixed. So therefore alpha BC is 0. Let's call this equation 4, with 3 being the equation which we have written here on the top. We can now combine equation 3 and equation 4 in the sense that we will substitute AB over here and we will get the equation, we get this equation. As already mentioned, omega AD is simply omega 2 E2 prime. Omega 2 is given here on the left to be omega 1 as found during the velocity analysis, while E2 prime is in the negative E3 direction. So that omega AD is actually omega 1 with a minus sign along the E3 direction. We have already written down something for alpha D, alpha AD. It is along the E2 prime direction, which I just said is along the negative E3 direction. RAD can be seen from the figure on the left to be D by 2 along E1 prime. E1 prime is along the negative E2 direction, so this becomes minus D by 2 E1. That's RAD. I also need RBC. So this is given here on the left to be of length D along the negative E3 direction. So I will get, what more do I need? Oh yes, omega BC is given to be omega 1 along E1, omega 1 along E1. I also need RAB, which is this vector, and this you can find will come out to be 3D by 2 along the NAB direction. NAB is given here on the left. So now I can take this information that I have obtained and this one and put it all back here in this equation. So I will finally obtain a simplified version of the equation, which will be I get this equation for the unknowns alpha 2 and alpha n AB. You may be wondering how come alpha AB cross RAB became alpha NAB cross NAB. Is actually clear. If you take alpha AB, let me write it over here. Suppose I was to write alpha AB as alpha AB along the axis plus alpha AB normal to the axis, where alpha NAB is given here on the left by this formula, just as in the case of the velocity analysis. Then this component cross RAB will be 0 because NAB cross RAB is 0. They are both in the same direction. So therefore from here you will only pick up the contribution of the component of the angular acceleration normal to RAB, which is what I get over here. So I now need to solve this equation for these unknowns. You can do a quick counting. This is actually one unknown and this is two unknowns only, because it has to lie in a plane normal to NAB. This is a three-dimensional vector equation, so these are three equations. So I can now solve these three equations for the three unknowns. As in the case of the velocity analysis, let's call this equation star. Then to solve alpha 2, we simply take the dot product of star with NAB. When we do the dot product, the contribution of this term goes to 0 because this term is normal to NAB. When we do that, we will find that alpha 2 here on the left is given by minus 33 omega 1 square upon 8. So alpha 2 is now known, and once I know alpha 2, I can go ahead and solve for alpha AB n by taking the cross product of star n to find alpha AB n, which I have done so here on the left again. You can carry out the calculations. Hopefully the ones I have over here are correct. Thus I have solved the problem. I have found alpha 2 and alpha AB. Alpha AB has been found to the extent that I do not know what is the rate of spin of the rod AB about its own axis, because that cannot be controlled by this mechanism, as the joints A and B are spherical. So that completes this example. We will now move on.